Hi everyone, in today's video I wanted to talk about a subject that I've been researching more and more recently, which is kind of alternate architecture on the transformer, or like changes in the core softmax attention type of architecture. I've been reading about MEMBA, about linear attention, and also about the flash attention mechanism that make use of the GPUs. And I think like there's something there that is pretty interesting in terms of where the LLM will be going in terms of scaling, because these techniques effectively allows a large language model to have a much wider context length in the input. So in this video, we're gonna look at the research made by MiniMax, which are currently sponsoring this video, which I find absolutely awesome that like an AI lab company is sponsoring this sort of channel where like I literally just go and read the paper. So this is pretty cool. It's an AI lab that was founded in 2021 in China, in Shanghai. And as we're gonna see in the paper, they're like very pro open source. So for instance, like the model that we're gonna see today is actually open weight. So you can go ahead and like do whatever you want with it. And it's MIT licensed. So like if you have a commercial application of the model, you can actually do that yourself. There's the text version of the model that is open weight, and then the multimodal, so vision and text version also. So the model that they've put forth in this report is a linear attention model, kind of a hybrid linear attention softmax model that is on par with like the current closed source and open source model, but has a context length that is kind of massive. It can handle up to 4 million. And they show exactly how they can arrive at such a model. They are making use of lightning attention, which is a method that was published in 2024, but now they've taken it and then they productionalized it to a scale that is on par with the rest. So I'll also be mentioning a lot of the other literature. I've put like a full description about all the papers because this is kind of a culmination of a lot of the trends in deep learning that like they were able to catalyze into like a big open source MIT model. So the paper is called MiniMax-01, Scaling Foundational Model with Lightning Attention. Fairly comprehensive, like I said. You can here we have like the model architecture. It's a mixture of expert with the linear attention module embedded in it in a specific kind of hybrid topology. We then have like all the computational optimization they've done in order to make this work. And this take a lot out of flash attention and rig attention type of mechanism. We have the full pre-training, post-training recipe, and then we're going into like the vision language modeling that they've done, which is making use of like their text V1, and then they add the modality. It's really cool how you can see how you can take a train big language model like this and add a modality on top of it. So if we take a look at like a broad overview about what's the architecture about, at the center of it, it's a mixture of expert model, like all of the big models these days. It's a mixture of experts. So you have multiple network like this, and you have a router that is able to decide which expert they will use for this. So in the model cards, you're going to get like the number of billion of parameters and the active parameters that are there, because not all experts are used all the time. So if you look here, like we see that it's softmax is still there, like it's not gone and then we change it for another type of attention mechanism, but it's only used once out of X number of block. In this case, it's once every 8, because here it will be 7 of these lightning attention block, which are much different than the softmax attention block. It uses a bunch of tricks that the linear attention mechanism are using. This hybridization of softmax and lightning attention is what created like a useful model in practice on par with the rest, and that has massive context length. If you look at like the difference between a softmax and linear attention, it's pretty straightforward. So over here you have softmax, and like it's basically how you're gonna do the multiplication of like the different matrices, right? So here you have the query, keys, and value matrices. You do query and key first, right? And you get this n by n, and then you do the n by n multiply by the n by d. So then you get your n by d, and this is your attention kind of matrix. The issue here and the bottleneck is this thing. It's the n by n. computing this is what's leading to effectively like a big O of n squared times the time complexity for this algorithm. For all the linear attention kind of mechanism that exists, there's a few of them, like linformer, performer, like there's a whole bunch of them that have been developed since 2020, right? It's not something new. What you do is you do a trick where you multiply the right first, right? So if you have Q, K, V, you go K, V, and then you multiply by Q. So here you have K, you have your V, and you only get a D by D, right? That's smaller than an n by n if like this dimension is smaller. And then you do this multiply by the Q, and then you get to the same result, but smaller. The issue is in the softmax, because the softmax kind of makes doing this not really the same thing. So there are many ways where you can replace the softmax by something else, and it's just kind of weird, right? So in a nutshell, that's the attention. So like if you remember all of your computer science class, so which algorithm is better if you have an n square and this one is bigger, and then here you have d squared? Well, this one theoretically should be strictly better. In practice, it's not the case, but we'll see that in a few. So they decided to use a mixture of expert, right? And just because it's just more efficient, right? There's a many efficiency that goes into like these models, these transformer, like big architecture models. The mixture of expert is one that has been shown time and time again to be more efficient and less computationally intensive than just having like a very dense layer all the time over here. It makes training them like it's a trip, right? If you try to train a mixture of expert system, it's a big undertaking. But what's cool within this paper, like they show how to do it, the scale that is fairly big. So if we look at the model card for this, like so the context length is extended to 1 million token, like on average, but it can handle up to 4 million token, like during inference time. So it's 20 to 32 times the capacity of like the leading model, and we're gonna see like a graph in a few. So we have 450 billion total parameters with 80 layers, right? And 32 experts. So we have 80 of these layers in sequence. The one interesting thing is that like there's kind of a practicality to not using linear attention mechanism, because all of the infrastructure usually is made for like the softmax thing, and there's a lot of optimization that can be done there. So this can run much faster. We're going to see it in flash attention too. They had to design their own inference architecture and training infrastructure to be able to do it with the linear attention mechanism they have, but actually hybrid mechanism, so that it was as optimized as a flash attention V2 type of softmax transformer model. So the type of like optimization we're talking about here is like more efficiency in the compute communication overlap. So a bit like the ring kind of methodology, but they did a twist on it and they call it the Varling ring attention. And then you have the linear attention sequence parallelism, plus they did some changes on that. You have your expert tensor parallel type of architecture. All of this to say that like there was a lot of thought being made into like not only making it theoretically better, like we saw with this, but also practically performant, because the practicality is very important here. So if we take a quick glance on the result, so the Minimax is in the red, right? And what we're comparing against, we have GPT-4o here, Claude 3.5 Sonnet, Gemini 2.0 Flash, the Qwen 2.5, DeepSeek V3, and Llama 3.1. And well, first glance, like it's doing pretty well. Like it's not always like the best model. Let's say this one in MMLU Pro is better, but overall, like this is not the same type of model. We're talking about like a linear attention model that now has catch up to kind of be on the same par as a softmax model. It has both the theoretical improvement and a practical performance that is quite good. And if we look at the multimodal version of it, right, over here, we still see the same trend that it's like doing fairly good in terms of up there in terms of improvement, right? And with this, one of the cool things, we have the full recipe to get a model like this going. The part that is very interesting is in the long context type of benchmark, which there are not that many of them at the moment, right? So like in the very long context benchmark, it's doing much better because an attention mechanism that is made for this. It's made for having this theoretical improvement that made it so that you can scale it linearly with compute in terms of the input length n. So if you look here, we have GPT-4 that at this context length, it kind of break down. So you see that some of them stops right here, right? Which makes sense because like they have a cutoff, they can't go past that. You see Gemini 1.5 Pro and Gemini 2.0 Flash. Their performance is okay up to a certain point, and then they slowly degrade because of the added context. But MiniMax is also degrading, but way less than all of them, and still maintaining like a performance that is quite good with a length of the input context length of 1 million. And if you look at like the latency, which is a very important metric for like consumer or like business type of application that you leverage LLM, this type of architecture is kind of faster. It's much faster as the context length is increasing, right? You see here the Llama 3 that is running like locally, right, on like this GPU. Same thing as MiniMax, like becomes slower and slower as we have way more input length. But this one seems to kind of be running a bit linearly with the context length. The other ones, I think it's fair to show them here. However, like they are through an API, so you have to take that into consideration too. If we go a bit more into like the background information about like why we're here, like why we're at the point where like linear attention is needed, and there's all this kind of like massive optimization that we needed to do in order to make it work. Like if linear attention was already kind of discovered and proved to be theoretically more efficient 4 or 5 years ago, why are we so deep into softmax right now? Let's kind of rewind back, and I'll link all of the paper in the description. But like the bottleneck, like I said, is in this n by n matrix. This n by n self-attention matrix is a bottleneck because it's quadratic with the input length. The bigger the input, the more this thing will be slow to compute, and it will just like drag on, and like it will explode a bit quadratically. So this is this issue, and then there's this little softmax that if it wasn't there and we didn't need it really, like this would have already been solved a while ago. But because the softmax was there, it made things a bit more complicated to like deconstruct a bit this this matrix and make it more computationally easy to actually calculate. In order to kind of like fix this up, there's kind of 3 ways that you can go. Like one of them is like just basically new architecture, and like the right product trick is also part of it, the thing that we just saw for the linear attention. So new architecture, I'm talking about like Memba, there was like performer, there was like linformer, there was like all kind of former, transnormer, a lot of them that you might not even know about, because like they're trying to kind of reimagine how to build a transformer while keeping the good stuff and trying to remove that thing that is quadratic. Memba are doing pretty good actually at the moment, especially in images from what I've saw. What actually happened, it was not like these were not a right avenue to take a look at. It was this, like the IO optimization was actually in 2022 was the thing that kind of made the whole field go even more into softmax than before, because there was more juice by going all in on softmax. If you haven't read Flash Attention, I greatly recommend it because it's simple. It's not very complicated. Effectively, what happened was that this part is quadratic with the input length, but when they actually timed where the things were slow, they realized that it was not in the math model that was slow. It was everything else. All of this time, right? It was not slow because like the thing were complicated to compute. It was slow because of not good utilization of the GPU. That was kind of it, right? Most of the time was spent writing to memory, which sucked. The core invention here that we are talking about in Flash Attention is let's just do this a bit better, right? Like there's a different type of technique, tiling, recomputation. But in a nutshell, they were keeping softmax and then the softmax attention, like normal vanilla thing. And then they just made an implementation with the GPU much quicker by trying to not write and read in the memory as much as possible. So this kind of win for a while. So we had a Flash Attention too, and then what it unlocked, right, when you have that type of optimization, you can juice up the context length a bit more. You can actually scale up the context length much more than the prior implementation. And you can see it over here. They increase the context length on like this very small GPT model to 4K. And it was not that there was a speed up still that was involving compared to the prior implementations. So this was applied to like these mega big model. And actually it was not this one. It's like another optimization that they did flash intention to with Dr. Tridao. The same ideas, and then they just kind of juiced up a bit more. What they're doing here is like better work partitioning and better parallelization to the worker in the forward and backward paths. Like there was a lot of engineering that could happen here prior just to be more efficient. So these efficiency now are priced in the performance of the current model that we see. There was other type of improvement that were done. One of them is ring attention when you have multiple GPU. We present a novel approach, ring attention with blockwise transformer, which leverage blockwise computation of self-attention and feed-forward to distribute long sequence across multiple devices while fully overlapping the communication of key value block with the computation of blockwise attention. I greatly recommend this video from Discover AI. Really good, very in-depth, and they have a nice example with the library that they kind of just take from the initial transformer to like the blockwise thing. It's really cool. But here the blockwise thing, you just think about it that there's different block for key value and queries, and then you just distribute this better so that the communication overlap with like the actual computation that you're doing. So you're wasting way less time here. So again, another kind of I/O optimization that the whole field has been going on. Then we get to lightning intention. So lightning intention, there's two papers that are very close in time, a bit like flash intention. There was the one, and then there was the version 2. So it was by Quinn over here, again by Quinn. And some of these lab members are actually working at MiniMax. So this is kind of why they kind of take that, and then like they were able to scale it. But in a nutshell, it's taking like the good stuff from linear attention, and it's taking the good stuff from the I/O and then combining them into lightning intention, which is like I/O optimized linear attention mechanism. So where MiniMax step in here is that they took this idea and then they scaled it up, right? And they tried to find the practical implementation of it, which like happened to be a hybrid with like softmax, to get a model that is on par with like the big ones with the benefit of lightning intention. So you see here, we aim to build a model that matches the performance of leading commercial model while providing a context window longer by an order of magnitude. So this is pretty cool. You can even test it out. We're going to do some test with some of the example that they provide in the paper at the end of this. So the result here, like I said, is a mix between softmax attention and lightning intention. In the paper, they also call it transformer, because in 2022, Quinn over here also made like the first attempt to lightning intention, which they call transformer, and then they open sourced that thing also. So you have the open weight for that stuff. So it's these blocks that are called transformer blocks that are in the system. So let's dive into that specific paper. It's not the paper that we're reviewing right now, but it's a source of like the core thing in it that make it work. So what I like in this paper is that they kind of outline the messiness of linear attention versus softmax, pure softmax type of model. So here, like they're showing that like, hey, despite the promise, none of the current leading large language model have adopted linear attention. They're asking themselves why. And then inferior performance, there is a gap. Like even in the benchmark, when you look at it, there's kind of a gap between pure linear attention and then like the softmax one. And we'll see in the paper with MiniMax, there is still a gap when you use pure linear attention. When you hybridize it, it's better, and you get like the benefit, and you get the best of both worlds here. And like the training speed is slow, which is a problem, right? Even though theoretically they're better, right, at inference time and whatever, when you're actually training them, because they don't process all of the optimization that was done on like the quadratic one, they're just kind of slower to train. Especially when you have like this thing, the cumulative summation operation, that are there when you have like kind of this causal modeling happening that you need to train on, right? So when you have that, you have CumSum, and if you have CumSum, like it's just going to be much slower. Like yes, there's theoretical advantage, but like practically the advantage is not there. So they're kind of useless in this sense. If softmax was faster, like the theoretical advantage of them don't help out much. So the core idea for this paper is that they're using this kernel trick, like the right multiplication trick I talked about, to accelerate the attention matrix. And then what they're trying to do is they're trying to go around CumSum. So they're going to do a kind of divide and conquer methodology where they're going to apply the kernel trick to a portion of the matrix, right, of the whole matrix that they need to do, and another portion they will just use the normal type of thing that doesn't require CumSum. And by doing this, with this enter and intra block kind of operation, they don't have to keep doing this very slow operation. They do this, and on top of that, they layer pseudo flash attention, ring attention mechanism so that like it's much faster on GPUs. So it's the IO optimization that we've talked about, plus like the clever linear attention formulation. Here you have the standard formulation, right? Q times the keys times the values afterward. In linear attention, what you actually do is like the keys and the value first, and then the queries. But then you take like your softmax or norm. Here in this case, no, softmax will not work. But this is kind of how you do it. And now they show that like if you do this, which is the normal type of thing you should be doing, this will have a complexity n squared times d. If you do this, which is the right product, right? Like this thing over here, you're gonna get like the complexity n d squared, but it's gonna be not GPU friendly. So theoretically better, practically not that good. So what they're saying here is that for linear attention, they're gonna use 2 blocks. The computation will be done on 1 block normally, and then another block it will be done with like the right product. And this kind of technique is called tiling. So they take equation 3 here, which is the normal stuff, and then they kind of unfold it over here. So you have the key V's, and then like you have the output over there that is making use also the queries over here. And then like by unfolding this, they are doing effectively the first block over here normally, right? And then the second block over here in the right product kind of form. And you can see it visually. And then there's this whole kind of technique of making sure that like you're doing as much computation as possible on the RAM, keeping the right stuff on the RAM so that you don't have to like write it back to memory. So this optimization is kind of baked in how they're calculating their linear attention. So if you look here in their kind of architecture, which they're in this paper, they call it the transformer LLM architecture. They're making use of SRMS norm here, not the softmax norm. And with that, and then with the gated linear attention mechanism here, they were able to construct the transformer LLM. Not gonna get into more detail on this for like this particular thing, but that's kind of the gist of it, is like there's 2 blocks and then they're able to do like the right stuff on the right block with this kind of divide and conquer type of strategy. If we take a brief overview of like the other type of optimization that they've done on the IO side, there's this expert parallel overlap. And in a nutshell is that like while they just create groups of computation, and while the things are communicating together, there's computation that is happening. That's kind of in a nutshell what's happening with the parallelization. So here, like you can see a bit more like where the things are wasted. You need enough groups when you split up the token across the expert here, so that you don't get this, like you don't want to get like wasted time, and you don't want to get as much idle time as possible. So there's like kind of a balance that they've kind of computed, so to make their training of their mixture of expert more efficient. So then they did a whole optimization on the ring attention algorithm. So they took it as base, right? And then they made no assumption about like the length of the sequence so that they don't get as much wasted computation. So then they introduced varlen, which means like variable length in here, so that you don't get as much padding here that is useless for your causal computation. This approach avoids the excessive padding and subsequent computational waste associated with traditional method by applying the ring attention algorithm directly to the entire sequence after data packing. The key modification is to transform the original causal computation to varlen variable length causal computation, and similarly convert the non-causal computation into varlen non-causal computation. And then they went into a bit more of a parallelization improvement spray. So this was like the old linear attention sequence parallelization algorithm, and then they changed it so that like you could actually parallelize much more. So here, if you see like the main improvement and difference is the local prefix sum calculation. Here they're doing a sum over here. They're doing this kind of global routing kind of algorithm that they are talking about to get all the information from every other computing unit, and then they can still continue to do their work. And effectively, they've parallelized these blocks like this, which in this case was not entirely possible. What you have to get out of this is that their mixture of expert implementation is heavily parallelizable. So it makes it very I/O input output aware. So it makes it able to train much better, which this type of stuff is already happening for like a normal quadratic attention kind of mechanism. So they cranked this up a notch just so that their lightning attention could be having both a theoretical benefit, but also like the practical one with like a good GPU utilization. So far, we made some good headways. I'm gonna go into the pre-training and post-training kind of methodology, and then we're gonna take a look at the result so that you can see how good this setup is. So here they're showing their initial pre-training methodology that they're using, and then they're fitting a power law for the training loss and critical batch size, just so that they can pick the right parameters, right? Because at the scale that they're training the model, like they have to have some power information, and then that's kind of it. So you have all of the normal stuff. They're using the Adam W optimizer here. They're using the Xavier initialization method. So fairly standard. In long context extension, right, for their pre-training, they're using like 3 stages, which they found what's much more stable to train this. By the way, this is really cool that like we get so deep a level of understanding about how to train such a model. It's not just like you have all the data and you jam it. You have to train it in like kind of a sequence in order to keep it stable. So here the training length is being increasing over here, and they are modulating how many short they have, how many medium they have, and how many long sequence they have, and it's given by that. Like below 32K is like short, and above 120K token long is it's getting long. And you see that the as we go down the training length, the stages, sorry, we're getting more and more longer tokens here. So that's it. At this point, this thing is pre-trained, right? And once it's pre-trained, you can like post-train it so that like it's actually usable and much better, a bit like we saw with like the R1 paper. So in the post-training, they're using, again, kind of a few stages, but the recipe they're using is there's SFT, supervised fine-tuning, there's the offline reinforcement learning, and then there's the online reinforcement learning. So if you look here for the SFT, we implement rejection sampling to generate high quality response by the expert, sampling multiple variations per prompt across different temperature settings to select optimal demonstration measure by the reward hierarchy, which is going to be used to do the supervised fine-tuning. In this, the offline reinforcement learning, they're using DPO, so direct preference optimization. And then there's like the online reinforcement learning. And in this case, they are using the GRPO algorithm. It's a bit modified, but like it's the same kind of idea. So they're modifying the weight clipping type of thing that we saw in GRPO. They're approving the KL divergent, which like start to look a bit kind of fancy here. KL divergence, there's many different implementations. I have a video on that if you're interested, about like 3 different way you can implement. This is a 4th one. And then they have the balance advantage estimation. A lot of like finicky things that they've done at the theoretical level to make sure that their thing is as stable as possible on the online reinforcement learning. So by the way, like online reinforcement learning, it's as much art than a science here. If you look at the PPO algorithm, if you look at the GRPO algorithm, the very different ways that they can be implemented, there's still a lot of like tweaking of it that you need to do. It's very hard to get consistent result with these things. All of this soup is then baked into a 5-stage for post-training. So you see, like it starts to get like kind of complicated. You have 3 stages over here, you have 5 stages over here, all of the different ways, all the different knobs that you have to tweak and test, kind of bunkers. And it shows you how like they're doing their different linear decay here. It's changing as it goes by. And then there's different sequence length that you're gonna give into here. There's different epochs that they're using, different batch size. At the start it's bigger and then gets smaller and then it gets bigger at the end. That's how they're doing the post-training. It's a mixture of all of this that they're doing on their created prompt dataset. So if we look at how they're doing the reward modeling for the offline and online RL, it looked like this. Nothing too crazy here. It's just that they embedded it all into like the same reward steps. So here we have they're looking for correctness, truthfulness, helpfulness, harmlessness. And this is how they're doing their safety alignment. And a cool thing that you have to keep in mind here is that For mathematical and reasoning tasks, we utilize early version MiniMax-01 to generate binary reward signal based on answer consistency. Programming solution undergo comparative testing in a secured sandbox environment with performance metric data from test case success rate. Pretty cool, right? There's a whole kind of engineering that has to be applied in when the model do something, right? You want to have a good reward, a clean reward coming back to be as deterministic as possible, right? A binary one, right? So this is, it always, like, even in the other paper that I've reviewed on this front, like it looks, this is like a few lines, but the engineering that need to happen when the model during its training need to kind of open up a sandbox environment, dump its code over there, like run it. It has some test cases. It go back with like a binary reward of like, was it good? Was it not good? And then it iterate on that. Like that's absolutely bonkers in my view. So then they have like this whole verification pipeline going on. They have a whole evaluation framework to assess compliance of like various things, including user instruction. So there's automated rule-based constraint verification system, and then there's human evaluation of key metric. So like there's also like human in the loop in this thing, like which means it was quite a journey, I think, to deliver this text-01 model. So that's kind of that for like the post-training and the pre-training section. We can take a look a bit more at the result, which were kind of happening before, but I've just like jammed them all together just so we can have a good overview. So if we look at the main result, MiniMax text-01 is doing good on the academic benchmark. As the context length increase with like this ruler benchmark, it's doing better than the rest because it was trained to do so, right? And because of the inherent lightning attention mechanism that it has, which the other model don't have. Here we can see the difference in model size here, right? And type of model, so softmax, lightning, attention, and hybrid lightning. And as you can see, the softmax like performance is like what it is, right? The lightning attention, if you look it over here, it kind of sucks here at retrieval, which is a problem, right? Like it sucks at the needle in a haystack type of retrieval task. So it's kind of one of the things that motivated them to use a hybrid lightning attention, because if it's not good at retrieval, it's a bit of a problem. So there's something deep about softmax in the transformer that is super important. So if we look at like the needle in a haystack, there's a good video on that. It's this guy actually that started this whole thing. He basically used a lot of essays, and then he puts like one or a few like what we call the needle in this haystack of text, and he's asking the model to retrieve that thing, and this is what he give into the context. So something like, hey, what's the best pizza in San Francisco? In like article from Paul Graham, it should be able to pull that out because this information is like not like the rest. Then we have like the training speed of various attention mechanism. So here we have a whole lot of them. We have softmax, lightning, hybrid, HGR-N2, and MEMBA2. And then they benchmarked this whole soup of model. And you can see like the softmax one, as the sequence length increase, it just tanks because of its quadratic computation problem. Well, the rest are kind of okay, like they're kind of still doing are still kind of linear. So you see here the lightning is kind of the most efficient in terms of like token GPU per second. Lightning hybrid is getting worse, right? Because of the softmax that is tanking it. But overall it has the best performance like we've seen earlier. And then they did a whole bunch of kind of tests, right? To see like what recipe would be the best, what like type of hybridization would be the best. So here you have hybrid Cosformer 2, hybrid HGR-N2, hybrid lightning, and the hybrid lightning is just like an overall good model here, especially in the needle in a haystack. So the retrieval type of task, you see the Cosformer 2 has some trouble over here. It's also the most efficient with the token GPU per second. There was also this whole journey that they did with like sliding window attention mechanism here, which can do linear computational complexity like the rest by adjusting like the window size, but still being a softmax type of attention mechanism. So they benchmark against that, which was pretty cool. So you see here they're evaluating a bunch of different window size. Roughly speaking, the hybrid lightning is kind of good. Like it's kind of much better, especially in a needle in a haystack problem. And then they did something that I found quite interesting, because like I said, the benchmark for like long context is not yet like as robust as the rest. So they constructed this the needle in a haystack kind of multi-round version of it here, multi-round needle in a haystack. So it's designed for retrieval task in long multi-turn dialogue context. So they construct haystacks of a multi-round needle in a haystack as history dialogue, where user queries are synthetic but explicit request of event description and creative writing. At the last round, the query requests the model to repeat the response of one of the history requests, and then this is like the right answer that you need to get out of. So the haystack spans from 2K to 1,000,000 token, and each needle request is injected at like 25%, 50, 75%, because like it depends like on the haystack where you are injecting the stuff. So if we look at the result on the English version and the Chinese version, we have here all of the different model GPT-4o, Claude 3.5, and the Gemini versions. As the context length increased, the MiniMax start to kind of dominate the other model. Here, the 2.0 flash kind of is close, but still after 1,000,000 token, it's the only one that is kind of left standing with good enough recall. And if you look at like this ruler, which increased the context length again, you get like the full breakdown that we saw earlier. It's still a very, very strong performance here, even at 1,000,000. So kind of has a knack for that type of large context length setup. Remember, like they've specifically trained the model to like be habituated to these bigger input context. Again, if we look at long bench v2, MiniMax is better here. Same thing here. On the easy, hard, short, medium, and long version of it, here Quen is very close, but it's still kind of on par. Overall, it's a better model in this benchmark. And then they did some in-house type of benchmarks that was more closely resembling what they were getting in their applications. So this is good. You see, like they tested a whole bunch of them. There was a lot of human in the loop. So you have like the general assistant capabilities, the hard capability, the creative writing, knowledge Q&A, instruction following, coding, safety, and long context. It's doing pretty good. I find it cool that they also tested the other model on that front. Some of them are really good. Like you see here, Claude is an absolute beast at coding all across the board. But it's MiniMax is not that bad either, right? It's pretty good, but it's well rounded in terms like of long context. So if you have one thing to keep out of this whole thing in terms of like the performance of this model, is like if you need to like dump a lot of information in context, it's really good, right? And there's a way now for making models both performant and have massive context. So we should see that growing again in the near future. And then what they did is they trained a multimodal model, which is now it's a VIT transformer kind of embedded into the thing. So they were able to tag this on the rest of their architecture to create the vision model that they have. So there was 4 stages that they went through, right? So there's the modality alignment, the enhancement of vision understanding, enhancement of user experience, and enhancement of preference. But it all starts with the MiniMax-01, and it goes into like these steps. So the training data set for this is almost 700 million unique image caption pair, right? There are some text in it, and then there's some visual in it. This is for the caption data set. There's also a description data set of 100 million image source. There's an instruction data set here, which is question answering based on like visual input. The architecture is very simple. There's nothing complicated about it. It's a vision transformer, 300 million parameters in there. There's a 2-layer MLP projector. Model is initially trained at a resolution of that much for 37 billion image caption, and is subsequently fine-tuned to that much for 1.2 billion pair. This is good. So the encoder achieved a 0 shot classification accuracy of 80% on the ImageNet 1K dataset. Pretty good. So the training recipe here, there's the modality alignment between like, it was trained on text, so now you have to align it with the vision stuff. They're using 80 billion token sample from our image description dataset. One thing to note here is that they haven't found We have found that increasing the image resolution does not yield improvement in downstream task accuracy. Therefore, all images are processed at a fixed resolution of that much to reduce computation costs. So this is pretty interesting, given that like they could have ingested like larger images here. Then the stage 2, they call it enhancement of vision understanding. So instruction tuning, right? It's basically instruction tuning that they're doing here. All the weight of the model are open to update, not just the vision ones, right? In this case here, it was mainly the visions. And in here is like both the text and the vision part. After that, you have enhancement of user experience. In this case, the data constructed for this stage is guided by an independent human label test set that prioritizes not only accuracy but also the overall quality in terms of user experience. Resulting data set comprised of 44 billion multimodal tokens and is trained for one epoch. That's massive. Like this part, the enhancement of user experience is a massive undertaking here. Like it's pretty crazy they did that. Then they have enhancement of preference and they use DPO. So this looks like their offline type of reinforcement learning kind of methodology that they're using. So they construct a training set of 40,000 image text pair throughout the following process: prompt selection, response generation, reward assignment, and pair construction. They're doing early stopping because, like, remember, when you're doing offline or online reinforcement learning, like it can go crazy, the model, so you have to do a lot of stuff. In this case, they're doing early stopping so that it doesn't overfit like crazy. And I think they are also they include a significant portion of pure text pair to the data set. I think so that the degradation in like the other modality, just pure text, doesn't happen. That's basically that. And like if you look at the result, we already seen it a bit, but in all of these benchmark, it's kind of not too bad in general. So it's good at visual QA here compared to like all these other models that are multi-model. It's good at it's okay at mathematic here, right? It's not the best one, but it's kind of close, except on this Olympiad bench. It's not doing that great. It's surprisingly enough not the best in long context for the multi-model version. Like GPT-4 is still the best in this case. It's still better than most of them, but it's still not the best here. So there's something happening versus in the vision setup versus the text setup. Let's dive into the actual platform, and let's try a bunch of their example. Right? They have at the end of the paper a bunch of examples. We're gonna try them out and see like what the result that we get at the end of the day. Here we are in their kind of interface. You can test out. Now I'm gonna give it the actual paper, its own paper. I'm gonna ask it to kind of summarize it with like a key figure and everything. So let's try it out. So here's the result. So you've seen the paper. It's like 60 pages long. And we have a nice summary here. It's pretty good. I've read it a bit, and like the key figure is like this one that we spent a lot of time on. Here it explains why the MOE is the useful one. It makes point out the hybrid architecture here. That figure was important to understand that. This is cool. They keep the needle in an A stack figure here. There's this optimization for the MOE that was done, so the EP-ETP, and that was pretty important in terms of context length. And they have another example here with this paper, the stream aligner efficient sentence level alignment with distribution induction. And you can see there's kind of this poster format that it's following, but it's kind of nice to do summarization. Well, now we're gonna ask it to translate this whole thing into French. I know French, so I will know if it's gibberish. So let's see how it does. Okay, and now we have it in French. Mise à l'échelle des modèles de fondation avec l'attention claire, traduction complète en français. I like that it added this part. C'est une série comprenant le MiniMax 01.0. Attention claire, c'est bon ça. Complexe linéaire, implémentation efficace. Mélange d'experts MOI, scalabilité, efficacité. It looks pretty good, honestly. Like it kept the same structure and it just translated it. So yeah, that's pretty good in terms of French translation. I'm satisfied. Let's test out the language, the cutoff date for the data. In 2025, what is going on with Canada and the US that is major for their trade? We're gonna say that it can't do web search. We'll see how it's gonna go. So if we look here, the cutoff is in May 2024. This is where the date is done. This is cool, but now this is all out of the window. Let's do the same query, but with web search. But check the news now, please. Let's see how it goes. Oh, this is cool, nice. I like it. It's optimistic outlook. The trade relationship between Canada and the US remains strong. The ongoing effort to address tariff and improve supply chain collaboration of renewable energy. However, potential tariff and trade policy uncertainty pose challenge that both countries are actively working to mitigate. I like its tone. It's actually optimistic, cautious, but give the right information at the end of the day. That was cool. And that's it for today. I hope that you enjoyed this pretty cool paper. Very dense one though. There's a lot of it's kind of you have to think about it as a coalescence of a lot of different research area, and on top of that they did a bunch of optimization everywhere. Still, I find it really cool. I found it that this is kind of what the field needs. They need this type of open transparency about how messy this thing is. If you take a look at it, the level of engineering that need to happen at all level is absolutely insane. And I think that it's important to understand that these models are being optimized in this manner. I think also the other thing that was very cool in here is I think there's a clear research trend in the optimization of both the compute, but also having better algorithm in general, a theoretical algorithm to calculate the attention. I think that this will open up much more context length for the input and break out one of the main bottleneck of the current system. We're going to see more and more both multimodal and text-based system that have a truly massive context length. And this context length then can be used in improving processes that require a lot of knowledge, right? Without necessarily disrupting too much the input. So you're gonna dump a lot of stuff, and in one shot you're gonna be able to do what require multi-shot in the application layer. So I hope this was useful. Don't hesitate to leave a comment if you have any question, and I wish you all a great week.